The moment you deploy that beautifully designed microservice, there's always that fear. It's the fear of the single point of failure. You can just picture it, right?
Right.
A customer's checking out, and these synchronous API calls are just flying everywhere.
To inventory, to payments, to the geo service.
Exactly. And if just one of those services hangs for, say, 500 milliseconds, or even worse, it just crashes. The whole platform can freeze.
It's that fragile chain reaction, the domino effect.
The ultimate synchronous domino effect. So today we are doing a deep dive into an architectural blueprint that is specifically designed to kill that fear.
Right.
We're looking at moving 5 core business domains. We've got company, identity, billing, courses, and enrollment away from that tightly coupled high-friction model.
And toward a resilient, asynchronous, event-driven framework, all powered by Kafka.
And the source material we're looking at, it lays out everything. The exact file structure, the event map, the security protocols you need to build this.
So the mission is pretty clear.
The mission is clear. It's about achieving what the source calls weak linkage between services, guaranteeing reliable delivery even when things fail, and just embracing eventual consistency.
And that last one is so important. The idea that the system is always responsive, even if the data takes, a fraction of a second to fully catch up everywhere.
But that entire mission, it sounds like it relies on one foundational rule.
It absolutely does. This one rule underpins everything. Every single service is the sole owner of its own data. It has its own database, its own schema. It is its own source of truth.
So if the identity service updates a user,
then other services like enrollment or billing, they only consume that event to update their local cache or their own internal data.
Right.
They never ever write directly to the identity services database.
And if you violate that rule,
You've lost the whole game. You've completely lost the benefit of the microservice architecture. And this, right away, brings up the biggest technical hurdle. How do you guarantee reliable processing? I mean, how do you make sure your logic is correct, even if an event, due to some network glitch or a retry, arrives more than once?
the exactly once processing problem.
Exactly. And this blueprint successfully solves that, which is really the key that unlocks the stability of the whole system.
Okay, so let's unpack this. The first step, the necessary foundation, has to be standardization.
Without a doubt.
I mean, you've got 5 highly decoupled services. If they don't agree on how they talk, where their code lives, what their messages look like, you haven't traded coupling for resilience.
No, you just traded coupling for operational chaos.
Right. So the source starts with a really crisp standard for the Kafka topology. To keep monitoring simple and to manage access control lists, the ACLs, it recommends organizing topics by business domain.
So you get those core 5.
You get the core 5, company.events, identity.events, billing.events, courses.events, and enrollment.events. It's clean, it's predictable, and it's easy to secure.
And for operations, you need a couple of standardized additions to that. First, audit.events for centralized logging and compliance.
And second, and this feels really important, the dlq.topic.events, the dead letter keys.
Oh, they're your lifeboats.
Yeah.
Absolutely critical. When an event fails over and over, you pull it out of the mainstream so it doesn't block everything else. It just keeps the system moving.
That system stability really depends on the messages themselves, too. The source material is, it's insistent. It says message keys are mandatory. Why so strong on that?
Because the message key is your architectural time machine. It's mandatory because it forces ordering for a specific entity, what we'd call an aggregate.
Okay, give me an example.
Sure. So a user updates their password.
Yeah.
An instant later, they change their email. Both are identity events. If those arrive in the wrong order, your system is in an impossible state. But by mandating that identity events use the user ID as the message key, Kafka guarantees that both of those events for that specific user land on the same partition and get processed in the exact order they were produced.
So the key is basically the entity ID, company for company events, coursed for course events. It keeps the related changes together.
Precisely. And that's all supported by this unified event envelope, a structure that has to be identical across all 5 services.
We're talking about that critical metadata, right?
Yeah. Things every consumer needs. A unique event ID, the event type, the occurred at timestamp, who produced it, but most importantly, the hero of all debugging, the trace ID or correlation ID.
That correlation ID is an absolute lifeline when you're trying to follow a single action, like user signs up, as it bounces across identity, billing, and enrollment.
You'd be lost without it.
Now, stepping back from the wire format to the code itself, the the file structure. This is also heavily mandated. Why does the source insist on putting all the Kafka logic in folders like appin for Kafka?
It's just good architectural discipline. If a developer needs to tweak how a service connects to Kafka, you don't want them digging around in your core business logic or API endpoints. Right. By mandating a dedicated appin for Kafka folder with, say, producer.py and a consumer.py, you make sure that Kafka-related code isn't just smeared all over the application. It makes future upgrades so much simpler.
And that structure is also essential for the two most critical components we need to get to later, the idempotency guarantees.
Right. Every service has to isolate its publishing logic in an appin for Outbox folder and its consumption logic in appin framebox.
So that consistency means any dev can jump into any service and immediately know where the messaging logic lives.
Exactly. It reduces the cognitive load immensely.
Okay, let's get into the nervous system of this whole platform. You need to map out the event map, who owns what, who publishes what, and maybe most importantly, why another service even cares enough to listen.
Let's start with identity. It's sort of the access controller here. It owns user accounts, roles, permissions. So it publishes these simple but critical events. User created, user password changed, company user created.
Simple enough, but what about what it consumes?
So this is where it gets interesting. Identity consumes company created events. Now, why would it need to do that?
For authentication speed.
Exactly. If a user tries to log in, identity needs to instantly figure out which company, which tenant they belong to. So it uses those events to build and maintain a local, high-speed company domain cache.
So it doesn't have to make a slow cross-network API call to the company's service every single time someone tries to log in.
That is the definition of low coupling paying dividends. 0 milliseconds to resolve the tenant.
And it also listens to billing events, which I found fascinating. Things like subscription suspended.
Right. Identity knows nothing about payment processing. It just knows the final outcome might mean it has to block a user's login. It doesn't ask billing. Billing tells it.
So let's talk about that financial spine then, the billing service. It owns plans, subscriptions, limits.
And its most impactful published event, the one that causes the biggest ripple, is company limits changed. This could be about the maximum number of users or, say, the maximum number of courses they're allowed to have.
And that one event immediately triggers a critical chain reaction.
It does. The courses service, which manages all the intellectual property, the course and lesson data, it must consume company limits changed.
Why?
Because the system has to check those limits before it lets an admin create a new course. If the company is limited to 10 courses and they try to create an 11th, the courses service has to deny that action, and its knowledge of that limit comes asynchronously from billing.
And the same logic applies to the enrollment service, right? It's tracking student progress, but it also has to consume those same billing.events.
It has to. Its job isn't just to enroll students. It needs to check if enrolling one more student would violate the limits of the company's subscription tier.
And enrollment is also listening heavily to the courses service.
Right. It consumes events like course created to maintain its own local registry. That way, it can guarantee a course seat actually exists before it allows a student to enroll. No broken links.
So this map really demonstrates that low latency impact. A single subscription downgrade in billing instantly affects what can happen in courses and enrollment.
All without a single synchronous call between them. It's beautiful.
It is, but the functional map is solid only if the reliability is there. We keep coming back to this. Guaranteeing an event is processed exactly once. The source mandates two non-negotiable patterns for this.
The Outbox pattern for publishing and the consumed event, or inbox, pattern for consuming. They handle the whole end-to-end communication reliably.
Okay, let's start with the Outbox. How does that guarantee reliable publishing?
So when a service needs to change something, say update a subscription plan and billing, the sequence is absolutely fixed. 1, write the domain change to the database. 2, write the event itself to a special Outbox events table in the same database.
And 3?
3, commit both of those writes in a single atomic database transaction.
The atomic transaction is the key. It means the data change and the event either both succeed or they both fail.
Precisely. You never get an updated customer record, but a missing event. That's how you protect the business state. Then a separate worker process comes along, reads that Outbox table, and publishes the events to Kafka.
And that worker only marks the event as sent after it gets a successful confirmation from Kafka.
Right. So if the database crashes right after the commit, the event is safe and sound in that Outbox table. The publisher will just retry gracefully when things come back online. The business change is always preserved.
Okay, that handles publishing. But what about the consumer side? This is where the inbox or consumed event pattern comes in. What if a consumer processes an event, updates its data, but then crashes before it commits its Kafka offset? Kafka's just going to deliver that same message again.
It will. And the inbox pattern is what prevents that double processing.
Yeah.
It uses the local database as the absolute source of truth for what's been consumed.
So what's the sequence?
When a service gets an event, it first checks its own local consumed events table for a unique pair, the evented and the event type.
And if it finds that record?
It just skips. The whole process is skilled. The operation is idempotent. If it's not found, then it executes the business logic, records the event in that consumed events table, and then commits the Kafka offset.
So the order is critical.
The order is everything. By committing the offset only after the business logic and the database record are safely stored, you prevent double processing during rebalances or failures. You get that exactly once semantic.
That makes perfect sense. The database tracks the state of consumption, not just the Kafka offset. Okay, let's shift gears to security. A distributed platform like this needs highly efficient security, not just resilience. The blueprint uses JSON Web Tokens, or JWTs.
And the architecture is crystal clear on ownership here. The identity service is the sole owner of the JWT signing keys, both private and public.
Which means no other service can generate a valid token.
Or validate one without relying on identity's public keys. And securing that private key is, of course, paramount. The source is very prescriptive about this. The private key has to be in a dedicated secret store, like AWS Secrets Manager or Vault. If you absolutely must have it on the server, it needs 600 permissions. Only the identity service user can read or write it. Full stop.
And the magic really is in the public key distribution. This is what enables the speed and the decoupling.
Correct. The public key is distributed via a standard endpoint, get.wellknown.jdtaste.json. That JSON web key set format is the industry standard.
Which leads to this incredible efficiency win because the other services company, billing, courses, they don't have to talk to identity every single time a request comes in.
They don't. They check the JWT locally. They use a cached public key that they grab from that JWKS endpoint. This eliminates all those expensive synchronous API calls back to identity for every token validation.
So you maintain low coupling, high performance, and I guess if identity goes down for a bit, the other services can keep validating existing tokens.
Exactly. It maintains platform availability.
So we've mapped the architecture, we've defined the flows, we've hardened the delivery and security. The last piece of the puzzle the source emphasizes is consumer management. Every service needs a unique group ID.
Yeah, this is standard Kafka practice, but it's critical. It's how Kafka manages the workload and the offsets. If two different services, like courses and enrollment, shared a group ID, they'd think they were cooperating on the same job.
And one of them would miss events.
They'd steal messages from each other, basically.
So the implementation checklist is, well, it's demanding, but it's clear. You have to implement the Outbox and Inbox models in every service. Define your topics and ACLs, and set up dedicated systemed workers for publishing and consuming.
It's a lot, but the real strength here is how quickly you can get going with just a few MVP events. Something like company created and user enrolled. That's enough to bootstrap the 5 services and start providing real value right away.
Proving that a resilient architecture doesn't have to mean a slow deployment.
Yeah, exactly. This blueprint achieves high security by separating that key ownership and high performance by getting rid of those synchronous validation calls.
Yeah.
But as the system scales and you go from a few event types to maybe hundreds, and the volume grows to, say, 50,000 events per minute, it raises a question for you to think about.
Okay.
When services are reacting to thousands of changes per minute, does that principle of eventual consistency start to degrade into something more challenging? How do you architect for the auditing and state reconciliation you'd need when stale data becomes a constant reality and services might occasionally conflict over the truth they've cached locally?